So hello together. Today I want to discuss with you which steps must be performed to design a single-state amplifier. And what we learn to know is, in the first step, we learn to know Rollet's stability factor K, and this is of course an important factor. And the stability factor K can be calculated using this equation with the help of the S parameters. We, in the first step, calculated the stability factor using the Y parameters. And if I use the S parameters, the stability factor also must fulfill this condition for delta. So only if this condition for delta is fulfilled, then the stability factor is really valid. So, and as soon as I have this calculated the stability factor, I have in principle two conditions. One situation. This one situation is that K may be smaller than 1, and as a result then I can only calculate the maximum stable gain, which gives me an idea how much gain I can get with the help of the transistor. On the other hand, as soon as K is greater than 1, then we can calculate the maximum available gain using this equation. So this is the maximum available gain, and this maximum available gain will tell us what will be the maximum gain we can get from this transistor or active device as long as it's stable. And of course, if you want to design a single-state amplifier, the first step must be that we do the stabilization of our active device. Only under this condition, under the condition K greater than 1, a conjugate complete matching is possible. So this first step is to stabilize our active device, and of course the stabilization of the active device will have a certain influence on these both parameters. And then in the second step we will do the conjugate complete matching of the input and output. But of course here we will have the situation that as soon as I do the matching at the output, this will have a matching in the input and vice versa. So we have to perform this matching in more steps. And of course all these things today must be done with the help of the simulation tool, and now I will show to you how to use the simulation tool to perform these steps. So today I want to show you now how to perform the steps using the simulation tool. First we start with our unstabilized transistor, and here we have our transistor MG1302, and in the first step, of course, we can now have a look to the parameters. I do the analysis, and here we have the scaling parameter as 2,1, and now we are able to calculate also the maximum stable gain and maximum available gain. You have to tick this point, and then you see here the curve of the maximum stable gain and the maximum available gain. For K smaller than 1, the maximum stable gain is calculated, and for K greater than 1, the maximum available gain is calculated. And you see here this kink, and this is just the point. I will go to this point with the help of the marker, and we know that our transistor will become stable over as soon as the frequency is higher than 7.05 gigahertz. We can check this also having a look to the stability factor K, and you see here, you see that the stability factor K becomes now greater than 1, or in the dB scale, we will have here positive dB values. And we know that we can stabilize our transistor using a resistor parallel to the input, and this resistor parallel to the input we choose to have a value of 220 ohm, and of course we must connect this to the ground, and then of course we can now calculate the stability factor again, and then we see that the stability factor will be greater than 0 over the whole frequency range, which means now the transistor is stable over the whole frequency range. But we will also see now, if I have a look to the parameter, to the stable gain, maximum available gain, that now in this region the parameter is reduced and always the maximum available gain is calculated. So we see here now there is only a reduced maximum available gain to reach in the region of the former unstable transistor. What means that due to the resistor, we included the damping in this frequency region. And now to calculate, for example, to match the output, we can start, or we have to measure the output reflection coefficient at this frequency. So if I want to, for example, if I want to design an amplifier next to the frequency of 2.4 gigahertz, I will reduce now the frequency range from 1 to 3.8 gigahertz, which means now 2.4 gigahertz is just in the middle of our system. And if we do the analysis again and we have a look to the marker, then we see that at 2.4 gigahertz, we can in maximum reach a value of 14.26 dB as maximum available gain, which means we have to do the matching at the input and the matching at the output. And to do the matching at the output, we now must have a look, to the parameter S22. Do the analysis now, and we change our format to this Smith chart format or Smith diagram, and we can also use here the marker function to read out the value of our reflection coefficient at 2.4 gigahertz, and you see at 2.4 gigahertz we will have a reflection coefficient of 0.6214 and an angle of minus 35.81 dB. And in the next step we will use our simulation tool or to our Smith chart tool to perform the matching at the output. To perform the matching at the output, we use now our Smith chart tool, and we have as a point to matching. For matching, we have this point at 1. This means we have a 50 ohm impedance at this point, and we now go to the general settings here, and I already included here our reflection coefficient of the load. It's 0.625 214, and here we have the angel, and here we have the frequency where we operate, and the characteristic impedance of 50 ohm, and the goal resistance is 1. So we somehow must transform now our reflection coefficient of the output into this point. And to do this, we have here the Smith chart, the impedance Smith chart, but I can also switch to the admittance Smith chart. So this is the admittance Smith chart. And as a first element, we will now use a transmission line, and the red line now shows the possibility how we can transform using our transmission line, and we must transform to the one circle, the inductive one circle in the admittance plane. So we have here the inductive one circle at the admittance plane. And then we can use a capacitor to transform into our goal point, our goal, and here we now performed the transformation. We are now at our goal, and so we can now say end of transformation, and then this slide gives us the circuit we have to use. So we have to use a transmission line of roundabout 34 millimeter and a capacitor of roundabout 2.1 picofarad. And this we must now use, and these values we must use in our simulation tool, which we will do in the next step. We are back now in the simulation tool, and we can have a look, for example, again on the parameter S22. Of course, in the Smith chart or Smith diagram. So this is our parameter S22, and we can again use the marker to go to the frequency of 2.4 gigahertz. So here it's a marker, and now I will connect our matching circuit to the output. So I have to take a transmission line here first. This is always first an air-filled transmission line of air-filled. So here I must go here to 34 millimeter. So we have a 50 ohm transmission line of 34 millimeter, and we use a capacitor parallel to the input. Oh, sorry, not parallel to the input, but parallel to the output of 2.1 picofarad. And then we can perform the matching, the measurement again, or the analysis again. So here is our reflection coefficient, the analysis without our matching circuit. And if I do the analysis again, you will see that our marker jumps into the matching point. And we can have a look, for example, now to the parameter S22 in the log mag format. And you see that we will have here a wonderful matching of our output reflection coefficient of over minus 50 dB, which is quite high. And of course, then I can also have a look, for example, onto the parameter S21. So you see here the parameter S21. We have here already reached an amplification of 11.54 dB, but it's still not the 14 dBs we expect to get here. Of course, this is due to the point that, for example, now S21 is still not matched in our circuit. So in the next step, we would have to match also S21. And of course, as I already told you, the match of S21 will again have a matching influence on the output. So we have to perform this in several steps. And I just want to open now the final result, where we have the input and output matching. So this would be the final result of the input and output matching. Of course, the elements at the input and the output and the input change now. And if I do the analysis now, we will have a matching at the output, and we will have a matching in the input. And of course, now we are going to have a look of to the parameter S21, and we can take the marker function, and we can see now our parameter S21, which is equal to the gain of our stage, will be now exactly the predicted 14.26 dB, which we are already predicted using the maximum stable gain. And this is now the final result of the matching of our transistor. Of course, in a practical application, we still have to think how to realize the transmission lines and how to realize this capacitor.